Hi guys, this is Saurav here and welcome to yet another Aspire session for JEE Advanced 2019. As you all know, we are conducting a number of sessions so that your sailing to JEE 2019 Advanced is as smooth as possible. Until now, we have covered liquid solutions and electrochemistry, and this is the first topic of inorganic chemistry that we are going to take up, that is coordination chemistry, and we would be covering coordination chemistry in two parts. Primarily be taking most important questions, most critical concepts and mixing them together in the format the way JEE Advanced asks questions, like single option correct questions, multi-option correct questions. Primarily be focusing on multi-option correct questions and integer type questions. So those who all know me, I'm Saurav Goswami, and even so those who all don't know me, I'm Saurav Goswami. I'm from IIT Rourkela and this is my 10th year of teaching for IIT JEE curriculum, and let's start this session of coordination chemistry. And I would expect you guys to have a pen and a paper handy while you are watching this video, so that whenever there is a question which requires intensive writing, you can solve simultaneously with me. Okay, so the thing is, coordination chemistry is the most scoring part of the whole content of inorganic chemistry. There are so many parts: bonding, coordination chemistry, group study, but coordination chemistry is highly scoring because there is a lot of linearity. There's a lot of takeaways from the previous topics that we have already learned, that is chemical bonding. You have already read about isomerism, you have already read about nomenclature, but these things are pretty much advanced in separate topics. In this case, we take some few concepts, club them together so as to study most of the properties of coordination compounds. Isomerism is also not very difficult for these compounds, very simple. Isomerism nomenclature is also very simple. For people who have had problem in understanding coordination chemistry and few critical concepts of coordination chemistry, we had conducted one similar session for the JEE Mains as like the sprint program. Please do watch that video if you want to get some more clarification, some more questions, some more understanding of coordination compounds. So you have a total of coming up like about 3 videos, one of JEE Sprint which has already been done, and these 2 Aspire series videos which will help you to understand the topic in a greater detail. So let's start today's session with the first question, and which is this: which of the complexes exist in facial and meridional forms, or facial and meridional forms? So how do we identify what is facial and what is meridional? Facial and meridional represent a type of isomerism, a type of arrangement which is observed primarily in these kind of complexes. It is primarily observed in Ma3B3 kind of complex. In a Ma3B3 kind of a complex, which looks octahedral in nature because there are 3 ligands of one type, 3 ligands of another type, total of 6 ligands. So it will look something like this: M, A, I can put B over here, B over here, and B over here. This becomes an octahedral complex, and I can connect A like this. I can also connect B like this. If I choose to connect A and B, अगर हम choose करते हैं A और B को connect करने में, so it will be connected like this. Now it looks like a prime meridian. Okay, so if you look at the globe, there is a prime meridian. There are a lot of lines which encircle the globe from pole to pole. So this looks like a prime meridian. So this is known as a meridional or meridional. So MER represents meridional isomer. Okay. Another form is facial, in which the ligands will seem like they are present on the face of an octahedron. Now octahedron has 6 vertices and 8 faces. So let's try to draw it. B, B, and there's another B. Now, it will look something like this. If I connect A and A, it looks like we are considering one of the face of the octahedron. If I connect B and B, it seems like I'm connecting one of the face of the octahedron. So while taking the faces, it turns out to be a facial isomer. Okay, this is the premise on which we would be solving the question. So let's see how the question can be solved. So we start taking up the first one, CODIEN. DIEN represent a ligand which looks like this: NH2, NH, NH2. This is CODIEN2. अगर हमने इसके दो लिए, इसमें 3 donor sites हैं. You can see there are 3 donor sites. So how do we draw the structure for CODIEN2? CO, N, 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 okay, N, N, N. कैसे हम ड्रॉ कर सकते हैं? I can connect these two, I can connect these two, okay, I can connect these two, I can connect these two. Now if I take this, this one, and I take this one, it looks as if like they are present on a meridian. If I take just one ligand, एक ligand आप ले लो, okay, one DIEN ligand, so one DIEN ligand will be like this. So they look like they're present on a meridian. Let's take the other example. CO, N, 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 N. Okay, यहाँ पे एक nitrogen रहेगा. Now this can be connected like this. Okay, and this can also be connected like this. So now if I look at these 3 nitrogen atoms which are of one ligand, one DIEN ligand, if I look at these 3 nitrogen atoms which are of one DIEN ligand, they represent meridional and facial. So DIEN2 will be forming facial and meridional isomer. Ma3B3 ये तो रहेगा ही. Ma3B3, this will always happen. Let's look at the other examples. So COEN3. So COEN3, EN is ethylene diamine. It will look something like this: NH2, NH2. So CO, N, 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 N. So I can draw this part is represented by this semicircle or the circle. Okay, ये जो हमने बनाया है, this part represents this alkyl part, CH2. So it will be present like this. Now we do not have Ma3B3 kind of a arrangement. It will always be present like this. If it is present like this, it will never ever form meridional or facial, क्योंकि आप इसमें meridional और facial बता नहीं सकते हो. Okay, you cannot qualify it as meridional or facial because all these atoms look alike, and if you connect these three will be meridional. If you connect these 3, it will look like facial. If I take only one ligand, it will not turn out to be meridional or facial. So if I take just one ligand, it has to be tridentate for it to behave as meridional or facial. Bidentate ligands meridional और facial में एक बार में नहीं आएंगे. Okay, so let's look at the next example. COGLY. GLY is glycine. Okay, so glycine will look something like this: NH2, double bond O minus. Now it's a bidentate ligand, so let's see if all the different atoms. So what might happen? It's an unsymmetric bidentate ligand, unlike En, which was a symmetric bidentate ligand. It is an unsymmetric bidentate ligand. So CO N O. If I, let's say, write it like this. Okay, so I can draw this I can draw this. I can draw this. So I can see that the 3 nitrogen atoms are present on one face, 3 oxygen atoms are present on one face. Let's try to draw the other form. So it can be like this: CO N okay. I can do something like this. I can connect it to this. I can connect it to this. Now the 3 nitrogen atoms seem like they're present on one meridian, and oxygen atoms seem like present on one meridian. So we can see that unsymmetric bidentate ligands can generate meridional or facial, but symmetric bidentate ligands won't. So the correct answer to this question will be A, B and D. Okay, the correct answer to this question would be A, B and D. C would not form facial or meridional. Okay, let's move on to the next question. So which of the following IUPAC names are correct? This is a very easy question. We just have to look for the oxidation state and look for how they are written. So we start with the first one, K2OSCl5N. So I start with the positive part. The positive part is potassium. So we always start with the positive part of the complex. So first positive cationic part will be named, and then the anionic part will be named. So cationic part is potassium. I will name it as potassium. No preference to how many potassium are there. That is not even taken into consideration. If anything is present outside the square bracket, whatever be their number, if there are 2, 3, 4, 5, that is only utilized to measure the oxidation state, not utilized in naming the compound. So potassium, osmium, chlorine, N. So how do we name it? Potassium. Next, within the complex, first ligands. Ligands will be named alphabetically. So chloro, nitrido. Chloro का नाम पहले आएगा. So potassium. How many chlorine are there? Pentachlorido. Pentachlorido, because 5 are there. Pentachlorido, nitrido. Nitrido. Osmate, because osmium is present in the anionic part. So we will name it osmate. 6. Let's see if it is 6. So chlorine -1, potassium +1, nitrido -3. So what is the -5, -3, -8 +2? So this has to be +6. Only then the charge will be balanced. So this is correct. Potassium, pentachlorido, nitrido, osmate, 6, correct. Next, we look at this compound. Now this compound NHCN C5NH4 C5NH4, this entity is known as bipyridine. Okay, it's known as bipyridine. It looks something like this. This is bipyridine. C5 H4N, C5, H4N, two rings connected to each other. It's a bidentate ligand. Okay, so now this is a neutral ligand. This is a neutral ligand. आप इसके ऊपर charge नहीं देख रहे हो. Also, this becomes the cationic part. This is the anionic part. So पहले हम cationic को name करेंगे. But this is a bidentate ligand. Bipyridine name के अंदर में ही एक multiplicative term आ गया bi. So to prefix this, I will not use bi again. So if I use it as bipyridine, that will make it very clumsy. So I'll use the term bis or tris. Like over here there are three, so I will use the term tris bipyridine. Why iron? Because iron is present in the cationic part. This is the cationic part and this is the anionic part. So this is cationic, this is anionic. So if metal is present in the cationic part, its name would not be changed. If it is present in the anionic part, uske end mein suffix would be ate, like osmate. So tris bipyridine, iron, what is the oxidation state? Oxidation state is 2 because there are 2 chloride ions. So iron 2 chloride. So this is also correct. Next one. This entity is known as cyclopentadienyl. Cyclopentadienyl. It is an aromatic ion. This is cyclopentadienyl. It's an aromatic ion. It has a negative charge. So this ligand is negatively charged, -1. So ये अगर 2 units आपने लिया -1, so this का is iron का oxidation state +2 होना चाहिए. So it will be bis. What is this known as? This is known as eta. Eta represents the topology of the ligand. That means if I take the metal and the ligand and identify how many atoms of the ligand are equidistant from the metal, that will be given as eta. This is known as the hapticity. इसको हम बाद में कभी पढ़ेंगे. This is known as hapticity. Hapticity tells us how many atoms in a ligand are topologically or distance wise equidistant from the metal. So if I look at this complex, the complex would look something like this. It will look something like this. This is your cyclopentadienyl. Okay, this is an aromatic ion, and here you have iron. In this, all atoms are equidistant. All atoms are equidistant. Again, there would be another and all atoms over here are also equidistant. Since all atoms are equidistant, so it is written as eta to the power 5. If only one atom would have been closer, other 4 would have been far, then it would have been written as eta to the power 1. But it is out of experimentation, पता चलता है कि ये क्या होता है. So this is known as a sandwich compound. अब देख रहे 2 ligand के बीच में है. So Fe cyclopentadienyl, so it will be written as bis eta 5 cyclopentadienyl. Iron, because there is no charge on the complex, so it is cationic or anionic हमें नहीं मालूम, but it is neutral, that is for sure. Okay, it is neutral, and for neutral complexes the metal's name is not changed. So iron 2, like NiCO4, tetracarbonyl nickel 0. The last one is this PtPy4 PtCl4, cationic anionic. So इसमें platinum रहेगा, यहाँ पे platinate हो जाएगा. Okay, so tetrapyridine platinum 2, tetrachlorido platinate 2, because total negative charge is due to chloride or chlorido. Total charge is due to Cl minus. Total negative charge is -4. So total positive charge should be +4. +4 would be divided as +2 on one platinum, +2 on another platinum. So it will become tetrapyridine platinum 2, tetrachlorido platinate 2. Okay, 2 and 2. Our correct answer should be all of them. Clear? Let's move on to the next question. Okay, so let's look at this problem. Which of the following statement is or are correct? The transform of CoCl2 tri-N has 3 coplanar chelate rings. So since we are taking all multi-option correct questions, so it is important to know that these questions can be solved pretty easily. You have to take each statement one by one and proceed in the similar manner. So let's take the transform of this compound. Like if I take transform, so the easiest way to do this problem is to put chlorine in the axial position. So CO, Cl, Cl, and we do something like this. Now what is tri-En? Tri-En is a ligand which will look something like this. NH2, CH2, CH2, NH, CH2, CH2, NH, CH2, CH2, NH2. So we can see that there are 4 donor sites. If we have 4 donor sites, this is known as a triethylene tetraamine ligand, and if I have this ligand in a complex, so I can put nitrogen over here, nitrogen over here, nitrogen over here, and nitrogen over here. I can connect these two, connect these two, connect these two. Now what we have is this. So this is a chelate. Chelate means a cage kind of a formation in which the metal would be present in the center of it. So this is a cage kind of a formation. So we have 3 such rings in which there is a cobalt sitting at the middle of it. A similar structure is observed in hemoglobin. So there are 3 chelate rings which are coplanar, and this is the transform. So we have 3 coplanar rings in the transform, which is a correct statement. Let's look at the other statements. The transform of tetraamine dichlorocobalt 3 ion has a plane of symmetry as well as an axis of symmetry. So the transform of tetraamine dichlorocobalt 3 ion. So cobalt NH3 4 Cl2. So if it is 3 plus, this is minus 2, this should be plus 1. Okay, so how do we solve the question? If I take the transform again, CO, Cl, Cl, NH3, 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 NH3. If we have to identify whether it has a plane of symmetry as well as an axis of symmetry, what I do is I simply draw a axis through here. Later in optical isomerism you would learn a little bit about the nature of axis. This turns out to be a C4 axis. Okay, anyhow, so this is the axis of symmetry. About this axis, if you rotate, the same representation comes in front of you in one 360-degree rotation. In one complete 360 rotation, this form will be repeated. If I want to draw a plane of symmetry, I can take a plane like this. That will be the mirror plane, and one part of the molecule will mirror the other part. So this statement is also correct. The transform of tetraamine dichlorocobalt 3 ion has a plane of symmetry as well as an axis of symmetry. This statement is also correct. The next question is about oxidation state of the central metal in JEE salts is what? Let's try to look at what JEE salt is. So JEE salt is represented as KPtCl3 C2H4 dot 2H2O. Okay, it's one of the earliest organometallic compounds known. So in this, if I try to calculate this is ethylene. Ethylene has an oxidation state of 0, Cl minus 1, this will be plus 1. So this has to be plus 2 for the molecule to be neutral. Okay. Next, the D option is COH2O6 3 plus is paramagnetic with 4 unpaired electrons. This is pretty easy to identify. Cobalt in plus 3 oxidation state. So cobalt, if I take the ground state configuration, this is 3d7 4s2. In plus 3 oxidation state, it would be in 3d6 4s0 configuration. This is the way the orbitals will split in a octahedral arrangement. There is an octahedral symmetry. So 1, 2, 3, 4, 5 and 6. So there would be 4 unpaired electrons. Why we are following this and why we are not pairing up all the electrons is because H2O is a weak filled ligand. Okay, so if H2O is a weak filled ligand, we will have to follow this arrangement. If I follow this arrangement, we would see that cobalt turns out to have 4 unpaired electrons. Okay, so this statement also turns out to be correct. This is correct, this is correct, this is correct. So the correct answer should be A, B, C, D. Okay. So let's look at the next question. So if for a complex PT-NH3-6Cl4 the ligand substitution reaction is carried out with ethylene diamine, then which of the statement is or are correct? Now you have to understand that when ligand substitution reactions take place, then a ligand will be removed and a similar ligand or some other ligand will come in, but what would be conserved is the secondary valency. Now if I look at platinum, the secondary valency is 6. So it is imperative that with every reaction until the end, the secondary valency is conserved. Now if I take an NH3 ligand is a monodentate ligand. If I replace it with a bidentate ligand, so one bidentate ligand will replace 2 monodentate ligands. That's fair and simple. One bidentate will replace 2 monodentate. One tridentate will replace 3 monodentate. One tetradentate will replace 4 monodentate. One pentadentate will represent 5 monodentate, and so on and so forth. So we have 6 monodentate and we are performing ligand substitution. If we are performing ligand substitution in a stepwise manner, and this question is on the stepwise process which will happen. So in how many steps I can replace all the ammonia ligands? Can you guys tell me? If I have to replace all the ammonia ligands, then how many steps of ligand substitution should occur? So if I take PTNH3 6Cl4 and I only take the coordination sphere, I need to perform how many ligand substitution reaction to obtain PT? En whole thrice Cl4. We have to perform 3 reactions, or it will be a 3-step process. If it is a 3-step process, we are supposed to analyze the question on every step what is happening. So let's look at what is the final outcome. So final outcome is this: PTEN3Cl4. The ultimate product can exhibit geometrical isomerism. Let's look at if that option is correct or not. So I can draw it like this: PT compound like this would be incapable of showing geometrical isomerism, because if you replace nitrogen from like this position to this position, or this nitrogen to this position, you will not see any change. So geometrical isomerism takes place due to restricted rotation. So when you replace an atom, place it in a different position, you should obtain a different appearance of the molecule. So if you replace the atom, आप यहाँ से इसको उठा के यहाँ पे रख दीजिए, nothing will change. Okay, so will exhibit geometrical isomerism, which is not correct. It will exhibit, however, optical isomerism. Okay, the ultimate product can exhibit optical isomerism, which is correct, because if I try to identify a plane of symmetry, it does not have a plane of symmetry. I cannot have a plane which can bisect the molecule into two equal halves. So this statement is correct. Out of the first and second intermediate products of successive substitution, only the first is optically active. Let's see what would the first structure be. So the first one would be one. So I better draw it again. So what would the first structure be? I take this and NH3 is kept over here. This is the first structure. I have replaced two ammonia ligands with one EN ligand. This will be the first intermediate. The second intermediate would be replacement of two more ammonia ligands. Now if I want to identify if it shows optical isomerism, क्या हम कर सकते हैं? We try to identify a plane through which will be passed through the platinum atom, and it should bisect the molecule into two equal halves. Let's see if such a plane exists. Yes, we can have such a plane. If such a plane exists, the molecule will be optically inactive. So out of the first and second intermediate products of successive substitution, only the first is optically active. First is optically inactive. Okay, first is optically inactive. So the statement is incorrect. Okay, third statement is incorrect. Out of the intermediate products, one of the intermediate products can exhibit geometrical isomerism. Can this exhibit geometrical isomerism? Do you think this can exhibit geometrical nitrogen? I don't think so. But if I replace nitrogen and I put them over here, this represents the trans arrangement. And if the nitrogen atom would have been here, as in like this, if the nitrogen atom would have been here and NH3 and NH3 would have been placed over here, it will show cis form. So this represents the cis form, the previous one was the trans form. So one product which is the second intermediate that will represent, or that will have geometrical isomers. So one of the intermediate product can exhibit geometrical isomerism, which is correct. Ultimate products exhibit optical isomerism, which is also correct. Ultimate product can exhibit geometrical, which is incorrect. So our correct answers for this question is B and D. Let's look at the next question. Okay, in which case the effective this should be atomic number. This should be atomic number. In which case the effective atomic number value is satisfied. Now the effective atomic number value or the 18 electron rule suggests that if the total number of electrons in the third transition series for the metal is equal to 36, the metal is usually stable. But that is followed rigorously for metal carbonyls, not always for every other compound, because if you take K4FeCN6 it is followed, but K3FeCN6 it is not followed. Okay, so it's a very elementary rule, very rudimentary rule. It's not very robustly followed for every complex. It's followed exclusively by metal carbonyls to a greater extent. Okay, so they try to religiously follow it. Now we try to identify in which case it follows the effective atomic number rule. So let's start with the first one. So Fe eta 5 C5 H5 whole twice. So we learned it earlier that eta represents the hapticity, 5 represents the topological reference of all the atoms which represent with respect to the metal, and eta 5 C5H5 is cyclopentadienyl anion, and this will be a 5 electron donor. Okay, it will be a 5. If it is eta 5, it will be a 5 electron donor. Let's look at whether it satisfies this arrangement or not. So Fe2 plus, this must have been Fe2 plus for this reaction to take place, so that this entity to turn out to be neutral. So Fe2 plus, iron is atomic number is 26. If you take Fe2 plus, it will turn out to be 24, and then you're adding how many electrons? 10 electrons. So it turns out to have 34 electrons, which does not allow it to follow the effective atomic number rule of 36. So this atom or this molecule does not follow the effective atomic number rule. Let's look at the next one, nickel DMG. DMG is dimethyl glyoxine, or when it combines with nickel, it is used for the qualitative determination of nickel ion. Now if you look at the structure for DMG, DMG is something like this: OH, OH. This is a dimethyl glyoxine unit, but when nickel dimethyl glyoxine is taken, so this entity appears in an ion in this form. Now the complex will involve attachment of nickel using nitrogen, not oxygen. Please do remember that it involves complexation of nickel using nitrogen. So the complex will look something like this: NOH. So here is somewhere where we would place the nickel. This is methyl, this is methyl, this is methyl, and be connected like this. This is the hydrogen bond which will hold. So DMG turns out to be a complex or a ligand which will donate a total of 8 electrons. Okay, and nickel atomic number is 28, iron, cobalt, nickel. 2 electrons are removed because this is Ni2 plus, so it will be 26 plus 8. This turns out to be 34. So 34, it will not follow the effective atomic number rule, or it does not have the nearest noble gas number of electrons that the nearest noble gas has. Next one is Mn2CO10. So this is a metal carbonyl. Metal carbonyls generally tend to follow the effective atomic number rule, but let's see how Mn2CO10 is present. So this is Mn, C triple bond. If you take MnCO5, the complex doesn't seem to follow the effective atomic number rule, because Mn is 25 and it receives about 10 electrons from 5 ligands, so it does not follow the effective atomic number rule. But to achieve the effective atomic number rule, it undergoes dimerization with another MnCO5 unit by forming a metal-metal bond. This is known as a delta bond. Okay, this is known as a delta bond, and it contributes 1 electron. So 1 electron contributed by towards each Mn atom. Mn 25 plus 1 electron from delta bond and 10 from the carbonyl units. So a total turns out to be 36. So this follows the effective atomic number rule. The last one, MnCO minus 1, obviously Mn25 10 plus 1, that will follow the effective atomic number rule. So the correct answer for this question should be C and D. Okay, the correct answer for this question should be C and D. This is our last question for the day, and this question involves, this is an integer type question. So please read the question very carefully. The question is, beryllium 2 plus and zinc 2 plus react with each of these ligands separately. They form complexes. What would be the total number of stereoisomers formed? So our objective is to identify that if beryllium reacts with the first ligand, how many stereoisomers are formed? Beryllium reacts with second ligand, how many stereoisomers are formed? If zinc does the same thing with the first one and the second one, how many stereoisomers are formed? And then what we'll do is we'll add all of them and give the final answer. So first and foremost, we need to know that beryllium and zinc, when they combine with any bidentate ligands, this ligand is known as benzoyl acetane, and this ligand is known as acetyl acetane 2. Benzoyl acetane 2 and acetyl acetane 2. Now, the difference between both of these ligands is that both of these ligands are unsymmetrical. Like one of them is symmetrical bidentate ligand, the other one is unsymmetrical bidentate ligand. You can see that this region is resonance stabilized, and this part and this part are symmetrical with respect to each other. While this region, we have a benzyl unit and we have a methyl unit. So we have a phenyl unit and a methyl unit. So we have a unsymmetric ligand over here, unsymmetric bidentate ligand, symmetric bidentate ligand. So what we do is if I try to take Be2 plus and zinc 2 plus, you have to remember that Be2 plus and zinc 2 plus form tetrahedral complexes. Okay, they do not form square planar complexes, they form tetrahedral complexes. Now if tetrahedral complexes are formed, geometrical isomerism is completely ruled out. So we just have to figure out whether they show only optical isomerism or not. Okay, so हमने सिर्फ optical isomerism पे ध्यान देना है. Geometrical isomerism is completely ruled out. So let's look at if benzyl and zinc's behavior is the same, they form tetrahedral complexes, and if benzyl's behavior with these ligands remains constant, we can like extrapolate that argument to zinc. So let's look at only for beryllium. So Be2 plus, if I draw it like this, O, there is a phenyl unit, there is a methyl unit. Okay, ये आपने एक लिंक बनाया. Next, you make something like this. Okay, why is it tetrahedral? Because if I connect these oxygen atoms, it looks as if the beryllium atom is sitting in a tetrahedron made by these oxygen atoms. Now if I want to take a plane which passes through beryllium and which bisects the molecule into two equal halves, can we have one? So if I take a plane like this, a plane which contains this whole unit and passes from this point, will we be having mirror images? No, because phenyl will not mirror methyl. So this plus one enantiomer, okay, this plus one enantiomer, if it reacts with this one, अगर ये सिमेट्रिक है तो यहाँ पे फिनाइल के जगह आप मिथाइल रख दीजिए, and then you try to take a plane of symmetry, it will always have a plane of symmetry. So with acetyl acetane 2, it will not exhibit optical isomerism, but with benzoyl acetane 2, it will exhibit optical isomerism. So if zinc also behaves in the same way, what we can write with, let's say this is ligand 1, this is ligand 2. So Be2 plus ligand 1, two products, and zinc 2 plus with ligand 1, 2 products, that makes the total number of stereoisomers to be equal to 4. So our answer for this question should be equal to 4. The only thing that you have to remember is beryllium and zinc will never ever form geometrical isomers. They will always form optical isomers with bidentate. They always form tetrahedral complexes, man. So if they form tetrahedral complexes, only optical isomers. Okay. So with this, we finish this session of coordination chemistry. The next session would be on using similar concepts but slightly higher difficulty level problems. But before leaving, I would just like to pass on this message to you guys that you have to work hard, and you have to work hard in silence, and your success will be the noise. Okay, so you take any particular person which has played a game-changing role in economics or in industry or in arts. They've always been silent performers. They've all been dark horses. You take Jeff Bezos for example. So Jeff Bezos was a guy who started Amazon with the idea that he'll sell books. Now he sells everything. So the thing is, you have to work hard in silence and let the success be your noise. Keep that thing in mind. And with this message, I will bid you goodbye, and I hope you learn coordination chemistry a bit. Thoda revision karke aaiye so that the next session will be even more exciting for you guys. So next session will have problems of slightly higher difficulty level. So I will again expect you to like go through this session as well as sprint का जो हमने किया है पहले उसको भी एक बार देख लो, and then next session में we'll just fire it through. Okay, so this is Saurav Goswami like signing off, and we'll meet in the next session. Bye bye guys.